Shouldn't be hard to find. It's right there. Linear combination of vectors. Okay. Again, vectors could be arrows in 2 or 3 dimensional space. They could be matrices. They could be polynomials. They could be continuous functions on a definite interval or whatever. But linear combination of vectors. Okay. Combination like C1, V1, it's a sum of multiples, okay? Here's a multiple of V1, here's a multiple of V2. This is a sum of multiples of V1 and V2, and we can go out as far as we want. So it could be like so, okay? So often we're going to want to express vectors, very often, I mean, all the time. So can W be expressed as a linear combination of V1 and V2? Well, this means can we find C1 and C2 such that they'll just say so that C1 V1 equals plus, sorry, C2 V2 equals W. Well, if V1 and V2 are vectors in R2, and we've seen this, but let's just make sure we really grasp it. Okay, well, so for example, if V1 equals the vector, excuse me, 1, 2, V2 is the vector 3, 1, W equals the vector 5, -9. Any numbers you like. Then we look for C1 and C2 such that C1 times 1, 2 plus C2 times 3, 1 equals 5, -9. Now, this equation can be rewritten I'll say equivalently we write this equation as 1, 2, 3, 1 times C1, C2 equals 5, -9. Okay, there it is. And we can verify this. We know, and we review what we did last time because we wrote this sort of thing out very explicitly, that this vector equation or matrix equation, because these are 2x1 matrices, is equivalent to the system C1 times 1, which is just C1, and 3C2 has to equal 5, and 2C1 plus 1C2 equals -9. So if you don't see that, it's actually not a bad idea if you're sitting there, have a pencil and paper, and just jot this down and do that yourself real quickly. You can rewrite this as a system of equations. And if you don't see how to do that, make yourself a note to go back and do it. So you totally understand this because it's critically important. Okay, so this is equivalent to a system of equations. And this is equivalent to the same system of equations because this says 1 times C1 plus 3 times C2 equals 5, which is the same thing. This says 1 times C1 plus 3 times C2 equals 5. This says 2 times C1 plus 1 times C2 equals -9. Well, 2C1 plus 1C2 equals -9. Here's our equation. And this equation can be solved by inverting the matrix. I'm going to try to write it down here. I didn't leave myself a lot of room. But I think I can get it in here. Okay, C1, C2 then equals the inverse of this matrix times 5 -9. Now, I'm not going to work that out because I'd probably screw it up, but there it is, okay? You can work out the details because you've inverted matrices 2-3 weeks ago. You can augment the matrix by the identity matrix and reduce it down so that this matrix becomes the identity. The identity, if you follow the row operations throughout, is going to then become the inverse. Now, that's something that you really need to have mastered because, among other things, there's going to be a midterm exam in about 2 weeks. Okay, so we're going to cover up through chapter 4. It's very foundational that you understand these connections, which is, of course, why I've assigned the written problems to make sure that you're seeing that. And if you aren't, to see what it is you're doing wrong, give you feedback, and help guide you through it so that you're going to be prepared. Okay, so really things kind of start with the idea of how this represents a system of equations, and this represents the same thing. If you see it here, then you pretty much see it. If you don't see it, you got to think about it until you do. Okay, so now I've gotten some written work, and in some cases, I think people are a little shaky on this idea. In some cases, I think they've pretty much got it, but everybody's shaky on a little something, which is to be expected. But right now, you need to start preparing for this midterm. Okay, so again, this represents a system of equations that answers the question of, can we form a linear combination of these two vectors that's equal to this one? This represents the same system of equations, and this is a matrix equation that can be easily solved. And when I refer to a matrix equation like this is what I mean by matrix equation. A times the vector x equals the vector b. So b equals A inverse times x. You can't do, you're not doing a reciprocal of the matrix because you don't have matrix reciprocals, but you do have matrix inverses. So this is just like an algebraic equation where you have AX equals B. You multiply both sides by the reciprocal, which is the multiplicative inverse. So it's reciprocal is an inverse. Okay. When you get to matrices, you don't have reciprocals, but you still have inverses. So there we have it. And this is just, first little taste of matrix algebra and matrix equations. So there we have it. And how do we know that this thing has an inverse? Well, we take its determinant. Okay, 1 times 1 minus 3 times 2 is -5. There's our inverse. There's our determinant, so we know we have an inverse. So this is going to work. This guarantees that if you follow the procedure for doing the inverse of the matrix, and of course you can just flip things around and change a sign or two and invert a 2 by 2 matrix. But if you have a 3 by 3 or higher, you're going to have to go through the row reduction reducing the augmented matrix, but there it is. Okay, so it's all old stuff, but we have to be aware of it so we understand how this matrix equation with the column vectors here and here gives us a solution that tells us that there is a linear combination and tells us what the numbers are here. This also guarantees that no matter what vector we have over here, we can do this linear combination. Now, if the determinant happens to be 0, we can't do this. And that means there is no linear combination. In the case of a 2 by 2, or in the case of R2, that would mean that one of these vectors is a multiple of the other. Okay, so I can make a couple of statements related to this. If the determinant of A is not 0, we can solve call it A times C1, C2 equals W1, W2. Make sure you understand where that comes from. If the determinant of A is 0, we can't solve, so there's no linear combination. No linear combination of the vectors that's equal. Now, remember that A is your matrix of column vectors. Okay, so we could say A is this square matrix. Okay, and of course, if A isn't a square matrix, well, either you have a problem or you don't, but you deal with it, okay? And we'll see examples of that. So A is your matrix of column vectors. These are the vectors, and you're trying to find the linear combination of these vectors that's equal to this vector, this W vector. In higher dimensions, and we haven't defined dimension, but just think Rn. Okay, so because any vector space over real numbers is going to be equivalent, it turns out, to vector to an Rn for some n. This works in higher dimensions. Now, when I say that, it's not totally true, but as far as what I'm doing here, it is. Okay, some vector spaces have structures that we'll see in the next chapter where you have inner products and a bunch of other stuff. And that's not true of every vector space, but all this is. Okay, and what I mean is any vector space over the real numbers is going to behave, at least as far as these questions are concerned, just like an Rn. So you can think of an Rn if you want. Okay, so anyhow, this works in higher dimensions. Okay, and of course, and I didn't say what I'd said before. I wanted to summarize this. Let me back up. Okay, if the matrix of, if the determinant is 0, you can't solve, so there's no linear combination. And I'll just have to use this space. And V1 is a multiple of V2. That's something you really need to verify for yourself. And it's simple. If you reduce a 2 by 2 matrix and you end up with a row of zeros, that's how you get a determinant of 0. And if you get a row of zeros, that happened because one vector was a multiple of the other. Okay. Okay, so again, now this works in higher dimensions, but you can't say, let's do this. If A equals V1, V2, up through Vn, and I'm about to say something that isn't true, so let me back up and think how I want to phrase this. Okay. If A is one of these, meaning, of course, you have n vectors, all of length n, think column vectors of length n. That gives you a square matrix. Then if you can invert A, then you can always solve matrix equation. AX equals B. For any B of length n, for X equals C1 through Cn. A little bit clumsy wording there, but it should be clear what this means in terms of this. A little bit of an inaccuracy up here. I'll come back and take care of that. There's one case where this can work. If V1 is a multiple of V2 and W1, W2 is also a multiple of either V1 or V2, then you can solve it, but not by inverting the matrix. And I'm not sure how I'm going to rescue that statement, but we'll get it in a minute. Want to look at this. Okay, so we should understand this. We know what this is going to look like. This is going to be n columns, each column of length n. So it's just going to be a bunch of call it A11, A12, A13, and so forth. Okay, an AIJ matrix. We can invert it. How do we invert it? We invert it by row operations on the augmented matrix, A augmented with the identity. And if you don't understand that, make yourself a note and go back and research it. Email me. I'll give you a quick explanation and a reference, but it's right there in your book too. So try to dig it out. Not that I mind answering an email, but you learn better if you dig it out. But if you can't find it, email me. I certainly don't mind clarifying it. Or look back at the videos. Okay. Okay, there. Okay. So again, where are we? We're trying to find linear combination of V1 through Vn that equals some vector W. That gives us an equation. A, where A is the matrix consisting of these columns. X is your C1 through Cn. B is your W vector, if you like. So okay, I'm looking at board spacing stuff. I didn't really want to do this, but this could be A11 through A1n. AN1 through ANN. That'd be your A matrix. Your X matrix would be C1 through Cn. And if B is your W vector, maybe that would be W1 through WA. We really want to understand this. You really want to understand the notation. You want to understand it in terms of problems that you've solved. You want to be able to set this up and then invert the matrix. Okay. And then we could say that the matrix A augmented by the identity matrix reduces to the identity matrix with A inverse. Again, just to remind you of the context. Now let's get back to the statement I've been trying to provide. Well, here is a perfectly okay statement. I'd like to have the opportunity to restate it just a little bit, but it should be clear enough. If you can invert the matrix, you can always find C1 through Cn. If you look at this, you see that I can take this matrix, do this, get this inverse, provided determinant of A is not zero, provided the matrix is non-singular, provided several equivalent statements that you really want to try to understand. Okay, so there are other cases. If you can't invert A, it means that there exists C1 through Cn, some column vector C1 through Cn, means that C1 V1 through Cn Vn, add up this particular set of multiples, gives you the zero vector. And that's equivalent to saying that one of these vectors, at least one of these vectors, is a linear combination of the others. And I want to say that, I have a little trouble writing it down low, so I'm going to do this balancing act here that usually works. So if I don't mess up too badly, the board won't fall and bruise my fingers. Okay, so this means equivalently, I could write it this way. V1 equals C2 V2 all the way out to Cn Vn divided by C1. Obviously, we can put all the other vectors and it should be negative of this. Okay, put all these other vectors on the other side, divide through by C1. Now there are a couple of caveats, the C1 through Cn can't all be zero, but it could be that C1 is zero. C1 is zero, then pick one of the vectors that has the coefficient that isn't zero and solve for that vector, and that'll work. Okay. This means that this set of vectors, in either case, is not what we call linearly independent. Okay, couple of caveats here. My statement up here. If A, the determinant of A is 0, we say that again, tells us that V1 and V2 are multiples of one another. Okay. I got it. I've got to say W would not be a multiple of V1 or V2. So as long as W is not a multiple of V1 or V2, we can't solve the equation. If W1, W2 is a multiple of V1 or V2, then of course we can solve it. If W is a multiple, the W vector is a multiple of the V1 vector, then I just let C1 equal 1, or C1 equal whatever that multiple is, and C2 equals 0, and you have it. And if it's a multiple of V2, then same thing. Okay. Want to understand this. Now let me rearrange this. And make another statement here. Okay, if we can't invert A, we can't invert our A matrix, then there exists a vector C1 through Cn such that the A matrix multiplied by C1 through Cn gives you the 0 vector. What's this mean? Well, if you think in terms of what this tells you, A is the matrix consisting of the column vectors V1 through Vn. This says that C1 V1 plus C2 V2 all the way out to Cn Vn equals 0. This linear combination of V1 through Vn is the 0 vector, and there's a condition that I need to have written here. Of course, there's always a solution of A times C1 through Cn equals 0 vector. Okay, and that is C1 through Cn equals 0. Okay, so there exists a C1 Cn not equal to the 0 vector. Such that A times C1 through Cn equals a 0 vector. Okay, so what this means is that this linear combination of the vectors v1 through vn is 0. And again, I say, I put a big lip on this structure here, and probably going to wrap my knuckles on it 3 or 4 times before I get used to it. Okay, there exists a linear combination of these that's 0, and I didn't write the word non-trivial. Okay, what I mean by non-trivial, there's a trivial solution of this equation if all your c's are equal to 0. That's your trivial solution. Okay, so there's a non-trivial solution, a solution where not all your c's are equal to 0, that gives you 0. Okay, that's a big deal. A little definition. Is a very important type of matrix equation where you have AX equals 0. Okay. This is equivalent to write it this way. A system of equations where each equation is equal to 0. You've seen this before. This is a set of homogeneous. Okay, so this is a homogeneous system. This is a homogeneous equation. The homogeneous equation is extraordinarily important, and you're going to see that almost immediately. And we're going to say if the homogeneous system has a non-trivial solution, then the vectors B1, which is your first column, A11 through AN1, let me write what I'm going to write here on a new column. I want to list a couple of conditions. These aren't linearly independent have a non-trivial linear combination equal to the zero vector have at least one vector that's a linear combination of the others. And you can't read that last little bit. Okay, these are all equivalent conditions. So they're all equivalent conditions. If one of these is true, the others are also true. Okay, very important. Okay, well, that's linear independence. And you have to sort through, some problems and understand this. You have to sort through some problems in order to really understand this. Remember, everything I've said can be pretty well understood in terms of this one example here. Okay. These two vectors are linearly independent because the matrix consisting of those vectors as column vectors is non-singular. Its determinant is not zero. This matrix equation can be solved for C1, C2. The matrix equation AX equals B, where this is A, this is X, this is B, can be solved by inverting the matrix. This leads, with a little more work, to really kind of very neat and very appealing picture of vector spaces. Okay, now let me take another quick look at your problem set, which I've kind of used, and where's the recording button? There we go. Span of a set of vectors is the set of all vectors you can get by combining. Okay, it's a set all linear combinations of vectors V1 through Vn. I think how much time we've got here. Example. Span of the set. V1 says 1, 2, 3. V2 is 3, 2, 1. And V3 is 1, 1, 1. Okay, span of vectors of this form. And of course, that would be C1 plus 3C2 plus C3. C1 plus 2C2 plus C3. And that'd be 2C1. And 3C1 plus C2 plus C3. Now let W equal W1, W2, W3. W equals this system. I don't want to take time to write out right now. Means this. So this equals this. And this is true for any W1, W2, W3, if and only if the determinant of the matrix 1, 3, 1, 2, 2, 1, 3, 1, 1 is not equal to 0. Well, it turns out that this determinant is equal to 0. If you row reduce this matrix, that's what you get. I don't want to, okay. If you row reduce the matrix, it's what you get, because if I add these two rows, I get 4, 4, 4. With these two vectors, I get 4, 4, 4, which is just a multiple of 1, 1, 1. So I'm going to say that 1/4 of this plus, sorry, something is wrong. Yeah, I wrote the matrix down wrong. Okay, got to fix it. I put the rows where the columns ought to be. It's careless. Okay, this should be 1, 3, 1, 2, 2, 1, 3, 1, 1. Okay. Now, if I add 1/4 of this row to 1/4 of this row, I get, well, If I add this row to this row, I get 4, 4, 4. That's a multiple of 1, 1, 1. So it's clear that I can reduce this to a matrix that has a column of zeros. So I can say that, and I hope I do this accurately. This matrix reduces to a matrix that has zeros here. If I subtract 3 times the first row from the second, I'm going to get a -4 here and a -8 here. And a -4 and a -8 dividing through by -4 gives me 1, 2. You can verify this if it's true, and you can fix it if it isn't. Okay. Then I can take a multiple of this, subtract 2 times this row from this one, and I get 1, 0. If I subtract 2 times 1 from 3, I get -1. Okay. So if I've reduced that correctly, I get C1 minus C3 equals 0, and C2 plus 2C3 equals 0, meaning that C1 equals C3 and C2 equals -2C3. And C3 is a free variable. And I'm going to pause for a second and write the rest of this out. Okay, again, I've abandoned my previous example. The mechanics there are clear enough, but where we're going, I didn't have time to complete the calculations, okay? Question, are these vectors V1 and V2 linearly independent? Now, these don't look like vectors, they look like matrices, but remember matrices, the set of all 2 by 2 real valued matrices does form a vector space, as you verified in the previous section. So are these vectors linearly independent? Well, the question comes down to this. Can you solve the homogeneous equation with, is there a non-trivial solution to the homogeneous equation? If there's no such solution, that means this vector isn't a multiple of this vector, and they are linearly independent. Okay, well, what does this system look like? This system looks like, well, C1 times V1 is just C1, 0, 2C1, C1, plus C2 times V2, 0, 2C2, C2, 3C2, And that becomes C1, 2C2, yeah, and then 2C1 plus C2, C1 plus 3C2, equals this. Okay. Well, then this means that C1 is 0, 2C2 is 0, 2C1 plus C2 is 0, and C1 plus 3C2 is 0. Well, this tells you immediately that C1 and C2 are both 0, and that's a trivial solution. So that means it's really easy to add a multiple of this to a multiple of this and get 0. And there's no other possible solution. Okay, this translates into the matrix equation. First of all, just set this column vector equal to this column vector. I don't need a 4-dimensional matrix. Okay. Okay. Translates to this. And of course, we can't invert this matrix, but we can solve this by matrix reduction or by any other method. And I'm just looking for space to do this here. I'll turn this upside down so you can't read what I wrote there. But this matrix clearly reduces to 1, 0, 0, 1, 0, 0, 0, 0. Which then translates to C1 equals 0, C2 equals 0. There's no non-trivial solution. So the system is linearly independent. If there was a solution to this, that would mean this matrix is a multiple of this matrix. Okay, this needs to come over here. This needs to come over here. I don't have any room on the back of this. Now, give me a second. Okay. This system is totally equivalent. If V1 equals what you get from this matrix, and V2 equals this matrix, you get the same identical equations when you get down to here. I'll just write it out. This yields a system C1 equals 0. C1 times this plus C2 times this gives you the 0. Two C2 equals 0 because C2 times V2, well, C1 V1 gives you a 0 here, and C2 V2 gives you 2 C2 here. And then this, which is totally equivalent to the system you would get here. And of course, these equations are the same as the equations that I wrote down the line here. Okay, so everything that we did here works here. And this question about these matrices becomes exactly the same question about these column vectors. So these matrices, in this sense, in the sense of testing for linear independence, becomes, and this system in testing for linear independence gives exactly the same thing. And in that sense, these matrices are equivalent to these vectors. You can do the same thing with any of the other problems that you're going to get in your next assignment. Okay, well, we're out of time. I'm sorry, things got a little screwed up there in the middle. What we did at the beginning is really critical. Make sure you understand all those critical things and then understand the operations that we used after that. I'm going to post another video to clarify some of this and work through some of the errors that I made. So look for that later today, assuming Zoom and my network cooperate. Okay. Again, apologies, and I will see you on Tuesday. Let me know if you have questions. I'm going to close now.